Welcome, everyone, to our fourth session in the series designed for both North Carolina and South Carolina DOTs. And today we'll be focusing on innovation in materials and testing. I do want to thank Tom for joining us today. Thank you, Tom, for being our expert perspective on this subject matter. Again, we appreciate your perspective. To review our series topics, we started with a cradle to gate perspective of concrete. We looked at the origins of materials from raw sourcing and extraction, as well as manufacturing of materials to the actual project site and to our concrete ready mix facilities. Then we looked at the evolution of customer expectations from both an end user perspective and a producer perspective. Our third session in the series looked at LCA and EPDs, or life cycle assessment and environmental product declarations, as a need for transparency around materials. And finally, I want to holistically close the series with how are we going to test our new materials that will constantly be evolving as we have new SCMs coming to market, as well as innovations. I do want to review the course purpose before we begin for PDH purposes. The series, again, aims to equip attendees with the knowledge needed to navigate shifting customer expectations, meet sustainability goals, and adopt forward-looking practices in concrete design, production, and project delivery. From a learning objective standpoint, today's session will look at identifying emerging concrete materials and technologies that are relevant to transportation infrastructure, including those that enhance durability, sustainability, and resilience. Explain how advanced testing, such as non-destructive testing, real-time monitoring, and performance modeling, can improve quality control and assurance in DOT projects. Describe the transition from prescriptive to performance-based specifications and how this shift supports the initiatives of all customers. Evaluate the impact of innovative admixtures, supplementary cementitious materials, or SCMs, and mixed designs on the long-term performance and life cycle cost of pavement and structures. Discuss how modern testing protocols align with DOT requirements for materials approval, construction oversight, and maintenance planning. And apply knowledge of material and testing innovations to improve project delivery, reduce construction risk, and meet evolving performance expectations in DOT-led infrastructure projects. Taking a moment again just to review where we started and where we are now from a course perspective. We've discussed the following topics, and these are really to give you the foundational knowledge to empower you to have conversations around benchmarking, around project delivery goals, and around new and emerging, not only expectations, but again, materials as the concrete industry adopts new materials in the marketplace. And all pieces are interconnected and essential to a holistic perspective. So I don't want to hone in on one particular area and leave out the rest, because again, they're all interconnected and very important to project success. So we started with looking at benchmarking from an embodied carbon perspective. How are we looking at our specifications to ensure that they're performance-based and not prescriptive, i.e. not restrictive? And then from an LCA and EPD perspective, those are kind of those end phases where we have documents and transparency for that third-party verification purpose. Now, in a private sector standpoint, these are absolutely necessary from tracking our carbon emissions from that carbon budget perspective. And in a public infrastructure standpoint, these are still very important so that you understand the type of materials that you're getting from your producers. Before we let Tom take the lion's share of today's presentation, I always do this, and from a strategic educational standpoint, it helps for reiteration of terminology because you will hear these terms often repeated throughout sustainability dialogue. And so embodied carbon is the total amount of greenhouse gas emissions, usually measured in CO2 equivalents or CO2e, that are associated with the production, transportation, installation, maintenance, and disposal of a product or material over its life cycle. And so from a building standpoint, again, if you're from the private sector, we're looking at all the carbon emissions associated with your materials and transport of said materials up until your certificate of occupancy. And that's when you start really calculating your operational carbon emissions. A carbon budget is always the maximum amount of greenhouse gas emissions, again, measured in CO2 equivalents, that a project can produce over its entire life cycle in order to meet environmental goals. GWP stands for global warming potential. You'll oftentimes see this reference in specifications. And global warming potential, or GWP, is a standardized way to measure and compare how different greenhouse gases contribute to our climate relative to CO2. And again, life cycle assessment, or LCA, is a systematic method rather, used to evaluate the environmental impacts of a product, process, or service throughout its entire life cycle, from raw material extraction to disposal. And so we looked at cradle to gate in the beginning of the series, and you can even take it a step further, specifically for concrete. One of the benefits of a cradle to grave perspective is that our product is recyclable, and it also absorbs carbon over its life cycle. And finally, EPD, Environmental Product Declaration, is a standardized document that provides transparent, verified, third party verified, and comparable information about the environmental impact of a product throughout its life cycle. So that's the document here to the right. You'll see it in different formats depending on who you're working with, but that's the standardized EPD from the National Ready Mix Concrete Association. So again, why are we looking at now testing? Obviously, carbon aside, life safety is paramount. And so when we start introducing new materials within our project, we have to ensure that long-term durability and performance are met, regardless of whatever your project goals are. So today we're going to look at new materials and mix designs, advanced testing methodologies, quality assurance and control, and what is your appetite for risk? So this is a more of a personal question, but testing can help lower risk and elevate comfort. And so from a human perspective, this helps us adopt new innovation while also being comfortable with the pace and adoption of said materials. So at this point, I would like to welcome Tom to kind of take control over the presentation and share his expert perspective on innovative materials and testing methodologies. Thank you, Tom.
Well, thanks, Jess, and this will be my first challenge, sharing, and I think you have to do something, right, Jess, so I can grab it?
I will make you a presenter now.
Awesome. I'd like to, again, I was telling Jess earlier how impressed I am that this whole series has been done. I think it's pretty remarkable that the DOT has done this, or has been participating in this, and it's great. And hopefully, I'm trying to. So I should be in presentation mode now. Does that look good?
Looks great. Thank you.
Excellent. And so yeah, as Jess said, I'm Tom Van Dam. I'm a principal at Wisjani Elstner. I've been working with, well, my career now, it's embarrassing to say, but I'm 40 plus years into working with concrete materials, a lot of pavement work, more recently bridge decks and other structures. And then it seems like these days a lot of data center stuff. Basically over the last probably 15 years or so, I've been working in the area of low carbon concrete with federal highways, with their sustainable pavements program and others. And so very, very interested in this topic and very enthused by it. I think it's important to go back in history a little bit and look at where we've come from. And I think many of you know the Romans are famous for their use of concrete. They are not the ones who discovered concrete. I think that goes back like 6,500 years, according to Google AI. But you can go to Rome today and you can see many amazing structures that are built out of concrete, including the Pantheon, the Colosseum, aqueducts, ports that are still in existence and still serving their original purpose. Some of them. So it's an amazing feat by the Romans. We kind of lost the technology over the Middle Ages, which is based on calcining limestone or marble to create quicklime and then mixing that with volcanic ash and aggregates. Modern cement was patented in 1824 by a British bricklayer. And basically, he achieved this by powderizing limestone and heating it in a furnace with clay. That the limestone provided calcium, the clay, the silicon aluminas necessary, along with a little bit of iron as a flux. And this basic material is the same today. It has changed a little bit, but we're still basically using the same material. In the U.S., we started using cement really about 1870s. The first concrete street was, I never pronounce this right, but I'd like to say it's yeah, what, Bellefontaine? I don't know, probably, but probably not. Ohio, 1891. The first concrete highway was constructed in Detroit, Michigan, on Dearborn Avenue in 1909. The pictures on the right are actually the oldest concrete pavement in Michigan that's near where I live, up in the Upper Peninsula, and it still exists. And that picture, the lower picture, uh, shows it more or less as it is today, and you'll see it's two-lift construction, which is pretty fascinating. Uh, Throughout much of the 20th century, we simply would take Portland cement, water, and make a paste and use that paste to bind sand and gravel together, sand and aggregates. We did start introducing early chemical admixtures, accelerators, and calcium chloride, some type A, low range water reducers, really around 1900. Air training admixtures were discovered by accident in the 1930s, and are used to protect against frost damage. And then really we started seeing a revolution in the 70s with the introduction of high range water reducing admixtures that all of a sudden allowed us to significantly reduce our water, which meant we could significantly reduce our water cement ratio to create much more durable concrete, or create concrete with really high slumps at relatively low water cement ratios. This allows us to pump the concrete and do things that we could not do even self-consolidating. Polycarboxylates, which are pretty significant, were invented in the 80s, but really started coming on strong in the 90s. And today, most of our higher end, high range water reducing admixtures are based on polycarboxylates. SEMs, or supplementary cementitious materials, they also have their own history. I mean, that's what the Romans constructed with, right? Pozzolana, which was volcanic ash from Mount Vesuvius. But basically, in the early 20th century, we started using natural pos, volcanic ash, diatomaceous earth, some calcined clays, a lot of dams and large foundations, including the Golden Gate Bridge, were used to control heat and eventually alkali silica reactivity. And then fly ash was started introduced around 1920s, and then became really common in the 70s and through today. And it's considered now almost a necessary component in many of our cementitious systems. So basically, just very, very quickly, modern concrete that we use in our transportation infrastructure. Typically, we're using coal ash natural pos between maybe 15 and 25%, or slag cement, and I notice that's in some of your specs now, typically between 30 and 40%. So this is commonly added at the concrete plant. Sometimes we're using ternary blended cements, or even other blended cements, such as a 1P is becoming common out west in some places. Uh, the type 1L cement really took the country by storm starting in about 2022. It's been used for decades in Europe and elsewhere in the world. And now, as we'll talk about later, most of our cements used in the US are 1Ls. Admixture wise, we use for most of our structures quite a bit of high range water reducing admixtures, viscosity modifying admixtures for pumpable concrete, flowable concrete. We're seeing mid range water reducers that could be still based on polycarboxylates for paving. And then you can use set modifying hydration stabilization for some applications. So a lot more chemistry is happening within our concrete than in the past. Specifications, acceptance testing is most often remains prescriptive. We're looking at um, basically air content slump, temperature when the concrete's delivered, and then we break cylinders typically for acceptance, sometimes beams. So not much has advanced on the testing front overall. So now I'm going to transition from history to where we are today. And I see most of this series was focused on this. So I won't go through this much other than state that, the debate over climate change and the role of CO2 is a political one, but the science is settled that we are putting a lot of carbon dioxide and other greenhouse gases into the atmosphere. And I think data will speak to this. We don't need to worry about models, but this is just historical data of where we have looked at. If we go to ice cores going back almost 500,000 years, you can see there's ups and downs in the CO2 in the atmosphere. But with the start of the Industrial Revolution in the 1850s, we just see this spike. And as we look at that spike, this is actual data collected on Mount Loa, Mauna Loa Observatory in Hawaii. Same place since 1958. And you'll notice that we just see this continuous climbing of CO2 in the atmosphere. It, if we look in the last year or so, this is what that trend looks like. And it's always creeping up. And I think if you look at these numbers, they're honestly very frightening. So 10 years ago, we were peaking at under 400 parts per million in the atmosphere. Now we're at around 425. And as of yesterday, we're at 424.6. Back in May, we were above 430. So this ever increasing amount of CO2 in the atmosphere is what we're concerned about. Oops, and I just shut off my light, excuse me. My wife has sent me to the basement because we got a wedding happening at our house this weekend, so I've lost my office space. Um, so basically, why are we concerned about CO2 in concrete anyway? And I know you guys have gone through this to great extent, but I just looked this number up this morning. Roughly about 3.7 cubic yards of concrete are used per person per year in the world. And we literally have built our civilizations, as the Romans did, with concrete. It has this large, positive economic and social impacts, but there are negatives from this immense use of this material. And so, roughly, we use about 120 million metric tons of cement in the U.S. every year, and or in 2023 specifically, and that links to about 1% of the US's greenhouse gas emissions that year. Globally, though, it's on the order of 5 to 8%, and it's expected to keep increasing as development continues in India and into Africa. So the concrete industry remains focused on carbon reduction. Uh, there are many states and local agencies that have by clean legislation. Private companies are very interested in this. I know that you heard from, I think it was Lithco earlier. They're committed to it. As I mentioned, I do a lot of work with data centers. That's where we're doing a lot of low carbon work right now, is with data center folks. And the industry remains. The associations such as the Carolina Ready Mix Concrete Association. Oh, I should have changed it. That's PCA is no longer PCA. It's the ACA, American Cement Association. NRMCA, National Ready Mix Concrete Association, American Concrete Pavement Association are all advocating carbon reduction initiatives and strategies. And this is also seen in our professional organizations such as American Concrete Institute, American Society of Civil Engineers, etc. So where do those carbon emissions come from? I think this has already been discussed at some detail, but the bottom line is if you look at this pie chart, most all, and this is the emissions in concrete, almost all of it, not almost all, but 90%, 85% or so is basically from making clinker in the kiln. And then we got the finished grinding. The raw grinding will also have some of that, a little bit of transportation. But when it comes right down to it, roughly 90%, 89, 90% is from the Portland cement. So just recapping, we make Portland cement by burning rocks and clay in a kiln at very high temperature. That kiln is using fossil fuels to create the burn, which is roughly responsible for 37% of the greenhouse gases associated with concrete, not just cement, but with concrete. The main rock, though, that we're burning is calcium carbonate. And if you look at that very simple chemical equation, and I promise you it's the only one in this presentation, you're seeing that we're decomposing calcium carbonate into calcium oxide, lime, and CO2. And that driving off of that CO2 is responsible for almost 50% of the CO2 in concrete. And so, on average, roughly we have 922 kilograms of CO2 per metric ton of cement that we produce in the United States. When we translate this to our typical concrete, and this is on average from NRMCA's numbers, you're looking at basically 236 kilograms CO2 equivalent per cubic yard, a strange metric, but that's always how it's done. It's the one time where we use metric and English units in one uh, measure. And almost 210 kilograms of that CO2 is from the Portland cement. So now I'm going to talk about the strategies needed. On the right is a cover off a new guide, relatively new, came out earlier this year from AASHTO. It is available, and it's on reducing the cradle to gate embodied carbon emissions of paving concrete, but it is applicable as well to structural concrete. Two of the strategies, the big ones, get Portland cement clinker out of cement. So that means we need to replace it with SCMs or entirely in some cases, as we'll talk about, or getting cementitious materials out of the concrete. So definitely, you can download this guide. This guide was developed with support of FHWA, and it was designed really to support the IRA LCTM grant program, which, if you've been keeping track of current events, has been eliminated other than the 5 states that successfully navigated it. Unfortunately, the Carolinas are not did not make the threshold or did not make the deadline. So, getting clinker out of concrete, cement optimization. Uh, the idea here is increase our SCM content through blended cements that we would purchase from the cement manufacturers or through adding more SCMs at the concrete plant. There are alternative SCMs and cements that are out there, but we'll talk a little bit more about SCMs in a moment. Optimizing concrete, basically, to do that, we really have to optimize our aggregate grading. And that's something that we'll talk about at the very end of this as we look a little bit at some of the specifications that you might be familiar with. But the idea is to optimize our aggregate grading similar to that we do with asphalt, minimize the amount of binder that we need for workability. This will actually give us better workability and reduce our shrinkage and create more durable concrete. So the way that we can optimize cement, getting that clinker out of the cement, is through those traditional supplementary cementitious materials that I've been talking about. Coal ash, we no longer just refer to fly ash because now ASTM C618 allows for bottom ash and fly ash to be you can grind bottom ash combined with fly ash or use bottom ash. And this allows us to actually harvest coal ash. Slag cement is one you're familiar with. Silica fume, I think you're familiar with based on your specs. And then natural pozzolan. So those are our basic traditional SCMs available to us. Limestone's really not an SCM, but limestone is often can be substituted up to a point with Portland cement, where you get an improvement in performance. And then as you add further limestone, you start to get a dilution effect, and you can start to see it, degrade performance a little bit to where maybe you get back to where you originally were. And then you have new coal ash sources are the harvested coal ash in ground bottom ash, as I mentioned. So these are all allowed under current specifications through either ASTM, uh, you know, C595 for blended cements, or their respective spec for each of those materials. We are transitioning more and more towards blended product. I think if you hear from the American Cement Association, they will say it's going to be their trend to put out more blended cements. The one that you're most familiar with is that ASTM C595 Type 1L. The 1L is a Portland limestone cement, but you may also start to see 1Ts, 1Ps, 1Ss. I saw that that was maybe a newly recognized cement that's coming into your region, which is a slag cement. Um, and then a new one coming out of ASTM is going to be a Type 1C. So that'll be out in the release of the fall ASTM standard for 595. And that will, I believe, up to 20 minimum 25% clinker, and after that it just has any other combination of pozzolan or supplementary cementitious material. So that one's going to be, I think, kind of a revolutionary binder. Getting outside of the ASTM C595 blended cements is ASTM C1157. This is not showing up, I don't believe, in either of your specs. It's performance-based way of looking at hydraulic cements, and it allows a lot more freedom for the person providing it. But and you would know what's in it because they have to tell you. But it would allow lots of other flexibility. And we've been working with a number of these products for data center construction, for example, where they're looking at significant reduction of 50, 60% off their benchmarks. This is an older chart. It goes through like to the May 23, just showing the increase in use of Portland limestone cement. Last I heard, we're at 63%. I believe it's kind of stabilized there, and it's we'll get to see where that's going to go in the future. Another type of cement that likely will begin to get used is limestone calcined clay cement. I'm not going to go into any details on that right now, but you may hear about it. It's, as you can see just in the description, typically you're looking at maybe 50% clinker, 30% calcined clay, 15% limestone, something of that type, or roughly. So it's a way to kind of balance out a further clinker reduction using a calcined clay as an SCM with higher blends of limestone that's very specifically designed to work within that system. There are a number of alternative cements that are getting a lot of buzz in the press. None of them are going to replace Portland cement in the near future. A couple of them are showing promise for scalability, and their business model seems pretty sound. Two general classes that I'll mention are clinker free and alkali activated. And so ones that are clinker free could be something like Brimstone or Sublime, where they have actually figured out ways to make effectively Portland cement without the need to burn limestone. And so that's really pretty exciting. There are others. You can see some are chemically derived, some are bio derived, biocements, different feedstocks, different processes. So it's a pretty exciting area. Um, Ones that are currently in pilot plant production, like Forterra or Sublime, is actually looking at a 30,000 ton per year production next year, and then scaling up from there. And I know that Brimstone is also considering pilot production in the near term. So some of these may make the market. I think what you're going to see first and more commonly are a number of these alkali activated materials. These could include geopolymers, which I'm not going to get into any detail on. They're non-hydraulic. They're basically a geopolymerization for alumina silica chains. But things like Secrete, the Ozinga products, uh, these are more slag cement based with alkali activators. And these are currently in production being used on projects. So I've been involved in projects with both. They do work. They work actually quite well, but they do have some of their foibles that I'll mention when I get to some of the case studies. So basically, when we look at what's coming at us with the cement systems, you have your basic toolkit that you're used to, having worked with over decades, and now you're going to see that toolkit changing a little bit. Some of that change you've already seen with the 1L cements, but you're going to see more changes there, I think, in the future. The other real opportunity here is optimizing gradations. And I want to say this started before even the thought of using it to decrease carbon, embodied carbon on concrete. We're looking here really to try to get a mix with great workability. A lot of work was done for the slip form paving industry, but it's now been extended for pumping concrete. And the idea, as I said, very simply is to pack more aggregates into our concrete mixtures of select sizes so that we need less paste. We need less paste, we can cut back on our cement, yet get as good or better workability. You can see this concrete mixer in the bottom right-hand corner of the slide, or I'm sorry, this concrete paver. That concrete is standing right up, and right behind that paver just slipped out beautifully without almost any need to finish. And so when people are paving concrete um, for these ultra smooth kind of pavements they're doing in the Dakotas and Minnesota and other places, they are using optimized gradations. They absolutely have to. Basically, and there's a lot of tools available to do this. The idea, though, is to move away from our traditional approach of thinking of concrete as having coarse aggregate and fine aggregate and setting up this gradation and then just, packing it with cement and altering the water to change the slope. So it is a different approach to mix design, but once you embrace it, uh, you'll find that contractors would not want to go back. There's a myth that exists that increasing cement content increases strength. You see it embedded in specifications time and time again. You see it embedded within the NRMCA benchmarking for the carbon footprint of concrete. But this is data from NRMCA, and it just basically shows that strength-wise, you're not going to see any market difference with increasing strength as long as water cement ratio is maintained. So what we need to do, focus on the water cement ratio and keep that the same. And you'll say, well, geez, we need more water to get workability. That's where aggregate optimization and the proper use of admixtures comes in. So you got to get away from this idea of believing that more cement is needed for strength as long as we can maintain our water cement ratio. This is just data from a project that I worked on a few years back. We designed a 500 pounds per cubic yard mix, which was 111 pounds below the Nevada DOT's minimum cementitious materials requirement. We paved that mix all the way into July quite effectively. You can see the 3-day uh, flex strengths here. But we were starting because it was July in Vegas. The heat was starting to get. We were starting to have some workability issues, mainly due to water control. And so they switched to the 611 pounds per cubic yard, the red dots. And you can see almost effectively no difference in strength. Maybe you could argue slightly higher on this 3-day, but take into account the higher temperatures. But at the 28 days flex strengths, you can see they're all really, really good. And if you notice where they're really, really high. So the one thing that to remember though, as we switch to new cements and new mixes, it is going to lead to different behavior. This, anytime you're switching a cement source, you should expect the behavior to be different. It's just that we have become so accustomed to those few cement sources that we have that now when a change happens, all of a sudden it causes the whole system to kind of come off the rails a little bit. Less clinker is going to mean we're going to generate less heat. This can be very, very helpful for mass concrete placements, but could pose a real problem in cool weather or where early strength is required. So that's one thing to be aware of. So really a new emphasis on the heat hydration is important, and it means maybe things like isothermal calorimetry might be something to consider looking into. It can create difficulties when finishing. We have slower setting. We generally have less bleed water. It can fool people. They can get on too early. They can trap bleed water. We see this problem emerging a lot on hard troweled surfaces where the crews that have developed this incredible empirical knowledge over decades are all of a sudden befuddled when they think the surface is ready to be finished and they get on it and all of a sudden they trap bleed water and we get delamination issues. So we've been sorting through that. Slower hydration can also affect when you can saw joints, when you can strip forms, when you can get on it, when you can drill dowel bars, tie bars, all of these things that have to be considered. And then less cementitious materials. This I think is really important. Um, as we cut back on the amount of cement we put in our mix, we have to control our moisture much more tightly. Often we have these really high cementitious content mixes because the ready mix producers have fluctuation, either water left in wash water left in the trucks, not monitoring and responding to changes in moisture content in their ag stockpiles, and those fluctuations in moisture at lower cementitious contents have a dramatic impact on the water cement ratio and therefore dramatic impact on strength. So as a hedge, it's easy for the concrete producers to put another 50 pounds, 80 pounds of cementitious in just to help give them more assurance on achieving strength. Man, that's really small, even to me. I don't know why. Anyway, path forward. So I'm going to talk about some demonstrations projects very quickly here. Um, but the main thing here is first thing is, as you talked about already, we want to quantify your embodied carbon to make sure that you're getting what you think you're getting. This is that whole, you've already talked about this to all your EPDs, essential step in making this happen. Getting your EPD benchmarking and then improving. Assess the availability of materials that are available to you in your market. Does you no good whatsoever to consider materials you can't get. And then move from the lab to the slab. Rigorous laboratory assessment is going to be needed. And not all labs are well equipped to address this. So that is going to be a major change that we'll need to implement. Then do demonstrations in non-critical places. Don't do your demonstration in the middle of the interstate highway. You know, you could pick a shoulder, you could pick a rest area, a maintenance yard. Start in areas that's not that critical until people learn how to work with these materials. Move from special provisions into specifications, and we're going to be moving towards more performance basis and then make continuous improvement. And I'm just going to quickly list these for sake of time, but we've done demonstration projects out at Minroad in 2022, and again last year in 2024. So lots of low carbon materials have been placed at Minroad. So keep an eye on that work. That work has all been published, is being published, and will be published. Those of you who are not familiar with Minroad, they've actually have taken a stretch of I-94, I want to say it is, outside of Minneapolis, and they built a spur off of it, a parallel running section of interstate where they just place all these experimental materials and then they run mainline traffic on it. And whenever they want to then go look at it, evaluate it, if they have a failure, they switch the traffic back onto the main line, and that allows them to do that. And it's a phenomenal facility. States participate in that activity through what's called the National Road Research Alliance, and a lot of great work has come out of Minroad. We've demonstrated low carbon on tilt-up construction, where we went out and used these mixes. And I want to just show these to point out the carbon reduction. So even our control mix had a 12% reduction off the CRMCA national average benchmark, but a mix with 25% slag cement was at 29%. But when we went to an 1157, that was basically 10% clinker at max, but an alkali activated slag, we saw these dramatic reductions. Uh, Basically, we did rigorous laboratory work again. All of the mixes were considered workable, but we found that placement and finishing of that mix 3 was going to be difficult. And it also had very, very low bleed rates and volumes and also very low heat. So there were some concerns about mix 3. And then, of course, when we went out and did our work, the temperatures were about 30 degrees Fahrenheit. And we did use standard construction practices. The goal was to tilt these panels at 3 days to meet spec, but we could not get the 3 day strength on mix 3. It took 5 to 6 days to get the necessary strength. All that being said, the crew loved mix 2. That was their favorite. That was the one with the slag cement in it. They absolutely loved it. They despised mix 3. Very difficult to work with. Um, we did use maturity. Match curing, though, was considered something to look at. In all of our future work, we're using match curing now. And then one takeaway was maybe have summer and winter mixes. It really was not a good mix to put down when the temperatures were near freezing. We did a slab on grade demo. Similarly, we had mixes where our control was a 9%, and then you can see these fairly significant reduction. Again, mix 2, you'll notice, is a slag cement mix. So low cementitious content all the way. If you look at these cement contents, 517 pounds total cementitious, but the slag right here, and then this one had a little bit of cement, and then this nothing. It's just the 1157. You can just see a lot of carbon reduction there. They all met, these are for data center applications. They met the hyperscaler data centers. This is AWS, Meta, Microsoft, and Google. Met all their criteria through the lab work. But again, bleeding was going to be a problem with the lower carbon mixes. And then screeding and moving those mixes was going to be difficult. They have a strange behavior. But again, standard procedure. We actually put this into one of our warehouse buildings where we tore out the floor and built test sections, traditional fishing, hard troweling, floating troweling, and whatever. The takeaway of this was that, again, the 40% slag mix was absolutely the favorite. It performed exceptionally well. The hardened properties have been great. The abrasion resistance is high. There was absolutely no downside that was observed with that slag mix. And so that was really something that was a big takeaway. So, kind of wrapping up now, I just want to talk about testing and quality assurance. The one thing to note is that as we switch to different mixes, different cementitious systems, as we start to reduce our cementitious content, you will get differences in the fresh concrete properties. The amount of bleeding, the rate of bleeding changes as we move towards more finely divided cementitious. Set times can be changed. It can be more sensitive to temperature. Workability, it's not just slump. We can get great slump numbers, but the mixes under vibration just will not, without vibration, just won't move. Some of these low clinker mixes. Air content has become really an issue, and it's not really understood why. We are doing a number of investigations right now. We're seeing high air in a number of cases. Um, there is some thought that maybe polycarboxylates, for example, are being ground as a finish or as a grinding aid during cement production in some cases, undocumented. But regardless, we are seeing some fluctuating air content, so I really encourage you to watch that and also start measuring unit weight in the field. It's a very simple test to do. You just need a scale, and that's a real good indicator if your air is getting high. And then heat of hydration is something that you might want to start looking more at. Hardened properties of concern. As I mentioned, early strength gain can be a concern with some systems. Um, Chloride penetrability, and I use that terminology specifically in that um, the we often use electrical methods, whether it's ASTMC 1202, which is a rapid chloride penetrability test, or resistivity, like bulk resistivity. But sometimes the electrical methods get fooled by the poor system chemistry in some of these systems. So uh, we may need to do more benchmarking where we do chloride ponding to at least then benchmark our electrical methods. And there could be other concerns like shrinkage, for example. Your testing needs are going to be highly dependent on the application. For pavements, we're going to have obviously different need than bridges. And for bridges, we're going to have different needs, whether it's a footing, abutment, a deck, girders. All of these things will have different needs. And it's kind of where that carbon budget comes in, where we apply that to a bridge. And therefore, we can really save a lot of carbon on the foundation, but maybe not so much on the deck. Um, Regardless, the material properties that result in good performance must be met. So there should be no compromise on achieving the properties that you need for long-term performance of your concrete. Uh, as I said, the fresh concrete properties in some of these real low carbon mixes can be a sticking point, especially if we move towards precast slab on grade construction where there's fouling. Pavements, not so much. Most bridge elements, not so much. Achieving strength is often the simplest thing to do. And always remember, strength does not equate to quality. And we need to measure it. We need to be assured that we get the strength that the structural design needs. But too much strength does us no good, really. And we've made this association that higher strength means higher quality, and it actually can lead to poor durability. And then early strength is really the one where some of these materials are very sensitive to changing temperatures. So maybe have a summer mix and a winter mix, for example. One thing I will say for structural applications that we're finding very useful and we're becoming major advocates of is match curing. This is getting away from, setting your cylinders on the slab or on the side of the road or even in a box, but instead, you have a specially designed box that monitors the temperature of the concrete in situ. It duplicates that temperature within the box. So, in other words, the concrete is cured at exactly the same temperature as it's experiencing in the field. And so, if you're looking at time critical structural elements that you need a certain strength to tilt it, match curing is a wonderful way to go. I did take a brief look at the draft South Carolina Section 701 specs. I won't dwell on it too much. I did note that you are looking at allowing the Type 1S cement. Uh, it's, which is a slag cement, and allowing up to 25% slag cement, which is pretty low, actually. Very safe number. Uh, my guess is that cement is going to perform exceedingly well. I will say there's no other mention of any Astro M240s, and so in other words, even your Portland limestone cement is not currently permitted to be used underneath that spec. Um, you allow F ash, C ash, but no call out for natural pause or even glass pause. And then your allowable aggregate gradations might be prohibitive to being able to even optimize your mix. You kind of have coarse and fine, but you're missing the intermediate fractions that would be needed if a producer, for example, had 3 or 4 stockpiles that they wanted to blend together to create an optimized blend. So that's something to think about. The concrete is specified based on strength class and in your prescriptive basis. Again, it's more cement equals more strength, and I would encourage you to rethink that. That's really not the case. And in other words, just really look at water cement ratio is probably your key parameter there. But more importantly, maybe move towards that performance based spec. So if you move towards performance, yep, you got to achieve your specified strength. Yep, you can have it at a couple of different times, as you do in some cases at 28 and 56, for example. Um, Basically, you're heavily relying on the bulk resistivity, which is a good test. But note what I said, that as you move towards more exotic systems, you may find that the bulk resistivity is not applicable. Another example is if you use colloidal silica as a additive, they will say that they change the pore solution conductivity and also makes the bulk resistivity not an applicable test. So something to consider. And then you're looking at other um, durability performance tests. So just some closing thoughts. Low carbon concrete is both a challenge and it's an opportunities. I think these opportunities are not just to reduce carbon, but really to create economical, available materials that we currently haven't looked at. Uh, Implementation challenge need to be addressed though, and we do that through, as I said, that process of rigorous lab testing and demonstration projects, slow rollouts through special provisions before adoption. Um, it's really a major shift in how we look at concrete, and all stakeholders are effective. All stakeholders have a role to play. And it's a pretty exciting time to be working in concrete, actually. It's a challenge, but it's also something where it allows us to innovate. And so, with that, I am done. Um, and we do have some time for questions if there are any. So, take it back, Jess.
I took it back. So let me share my screen. But thank you, Tom, for your perspective. Does anyone on on the line rather have questions? You can chat them in the chat function, or you can just come off mute and ask openly.
And questions are really good. I'm sincere about that. I love questions. So if I don't get any questions, I'll be very disappointed. Come on. If you don't ask a question, I'll ask one. No questions, Jess?
I'm not seeing any in the chat right now. I
No,
do.
I can't. Oh, go ahead. Go
Um,
ahead, Jess.
you mentioned maturity, and I know that some of our producers utilize maturity. How have your experiences with that particular testing methodology been?
We use maturity quite a bit. Maturity, if you're not familiar, is we put a sensor within the concrete and we measure the temperature. Um, we measure the temperature within the concrete over time, and we look at that combination of time and temperature. I think it's through what's called the Uranus function or equation, and basically related to strength gain. The problem with maturity is you do it during the mix design process where you establish the relationship, but if the mix proportions change in the field, or let's say the cement source changes, or the fly ash changes, or whatever, uh, the the correlation between your lab-based derived relationship and what is happening in the field is lost. So it's good. It's a good intermediate step, but as I said, what we find to be better is moving towards the match curing, where we actually would cure our cylinders, for example, in a match cure environment. And then if we need to drill holes right on it, tilt it, whatever, load it in some way, we break a cylinder when when we believe it's there, but we know that cylinder matches the strength in the field. So it's better than not doing maturity, but it does have limitations.
What maturity sensors did you use? You know,
Oh boy, we have boxes of them.
yeah, that's fair. Yeah, we were just. I was curious.
I'm trying, but I'm trying to think of the specific. There is one company that we use them all, but I would not say it's better or worse than any other. I, we buy them in such quantity. I think we must get a deal on them.
Okay.
Uh, but I don't know the name offhand. They're sitting in my colleague's office. Todd Nelson has a stack of them.
Okay. We can certainly find out later. And any other, Emily, are there any other questions on the line here?
Hey, Tom, if you don't mind, I'd like to just interject when you're looking at the performance-based specification for South
Yes.
Carolina. That's an ongoing process that we're in the middle of, and we chose to select a Type A, Method A, and a Method B because of if concrete producers did not want to go down the route of performance-based, they could always go back to what's normal. But the reality of trying to change DOT standard is very difficult. Those specifications are 50, 60 years old, and been built upon based on issues. So a two-line sentence in a specification becomes a four or five because you're changing it to address certain aspects. And they're also very stuck on the water cement ratio and the coarse and fine aggregate quantities to the point where it'll tell you what percentage of coarse aggregate you need to use in a mixed design based on the fineness modulus of the sand. So we're when we get into performance, and it's going to take a minute, but when we get there, then you can go in with whatever mixed design you want to use and combine the aggregates however you'd like to. Go to the cement content that you feel comfortable with, and they're going to drive everything by strength. So it's we're in the process of making that kind of a change in the DOT industry, and we'd like to continue to move forward with structural engineers and see if we can't grow that throughout the Carolinas as a much better way to design mixed designs that'll be effective, on projects. The other thing I have is, Type 1L has been a real challenge. Um, the I have a tendency to design mixed designs from the slab back to the lab. So, a lot of residential construction, you want to make a mixed design that the customer can work. With 1Ls, there are so many different changes in the way the cement chemistry behaves is it's hard for them to have any control over it. They could have an issue with set time or lack of bleed water or early strength development or a couple of different things that are causing cracks, early detrimental effects in slabs, and those kinds of things. And so um, I've been working on a lot of you know solutions to having five different changes in the cement behavior. Try to bring them all closer to only having one kind of a thing. But that's a real challenge right now is the transition into a 1L and the performance of the product in the field and with the concrete placement and finisher. So we're continuing to work on that as well.
I agree with you 100%. The challenge is real and it's hard, right? Because as you mentioned, our industry, and I've been doing it for 40 years, but it's been around a lot longer than that. We have developed our recipes and have used them with relatively good success, right? But unfortunately, we do have to change. We have different demands on our infrastructure, but we also have, as you mentioned, different cements. But aggregate sources have changed. Uh, there's been admixtures are changing. So change is hard for us, but it is something that as we learn more and we embrace it, we can find it can work to our advantage. I do think that your way of approaching it, both keep your prescriptive and then add the performance makes sense, right? That those traditional mom and pops, we'll call them, or producers that know how to make their mixes, they still have their path forward. But then you might be able to get someone who um, maybe has added some automation, better moisture control, different techniques, wants to blend, wants to add an extra bin or two stockpiles. They would have the opportunity to do that. And I think what you'll find is they'll become more cost competitive. And when they do, the market then will help bring about the change. So I do think it's important not to isolate people from the marketplace who have been contributing to it for a really, really long time, but allow them to be incentivized to to learn and to change. I agree. There's no easy answer, and there is no universal problem with 1L. I'm dealing with 1L all over the country, just like I deal with 1-2 all over the country. And there are differences, and we have had problems in some places, but overall, there is no problem, right, with 1L. We just have to got to learn to work with something different. So that's what it's all kind of about right now is we have some different things that we're working with. And I do think that as we move towards performance based, that as a DOT, it's a little frightening because you don't want to let go. But in the end, if you can measure the right things that give you confidence, I think you'll be happy. You'll get better products. Uh, the easiest thing is like optimization of the grading. Most people that have moved to optimized gradings, they'll say the quality of their products has improved markedly. Far less issues. And then the other one I think is and that fell right out of my head, so I don't know what it is anymore. But anyway, yeah, I commend you for making this effort, and going forward, I think it's going to pay off for you.
Tom, I have a question from Aaron on the line. Have you heard of increased scaling on bridge decks now that we are using more Type 1L cement?
There has been issues with scaling on some, not necessarily bridge decks, but I've seen it on. We got a big study going on in West Des Moines right now, looking at pavements. So, uh, have they been more than with the 1-2 systems? I will say that I've been doing durability and forensic work, and I didn't mention that I do a lot of forensics as well. Work with DOTs quite a bit and contractors. We might be seeing a few more instances, but it's not universally true. We saw scaling issues before. But the problem with that, I could see that would happen on a bridge deck would relate back to the bleed water, delay in bleed water hitting the surface. The mix appears all of a sudden, the contractor's expecting to see a better mix, so they start to overwork it to get it closed up. They might have a tendency to add water if nobody's looking, but we know nobody would do that. Uh, People have a tendency to want to use these evaporation retarders, which they are also now marketing as finishing aids, and they're 95% water. So I wouldn't say I would say you have to be more careful. You have to think about what's going on with that bridge deck with that 1L. There's a higher risk due to the bleed water issue, and yes, you could see more scaling. But again, I want to emphasize it's nothing with the 1L. It's how we're still learning to work with it, and that's where the issue is right now educating our entire industry on how to work with these new materials.
Thank you, Tom. I don't see any other questions on the line, so I think it's safe to say that we have closed out our session today. But again, I just want to say thank you for sharing your expertise. Thank you to everyone on the line for sharing your time and being open to learn about new materials and new testing methodologies today. Also, just as a closing statement, want to remind everyone here today well, it's not advancing right now. That's okay. Just a reminder to save the date for the Count on Concrete conference slated for January of 2026. But I will be emailing all of you a copy of the presentation, and all of the sessions in the series will be released. They will be online so that you can reference them at your leisure and utilize them from an educational standpoint. But again, thank you all, and I hope you have a wonderful day.
I wanted to add one thing, if I could, real
Sure.
quick,
Go ahead.
Jess.
Yeah, go ahead.
Invite Matt Fonte to your workshop.
Okay.
You know Matt?
I don't.
Matt Fonte, Fonte. Matt is an absolute guru when it comes to paving
Sure.
concrete, and he's a former contractor, and he is such a resource when it comes to helping DOTs and helping contractors in this transition, not just with 1L, but really aggregate optimization and quality paving.
Okay.
And so Yeah, Matt would be putting a plug in for a guy who I work with quite a bit. Um, he's really, really good.
Okay.
So I think you'd be happy to get him and have him speak to you.
Thank you. We'll definitely look into him for the Count on Concrete conference.
And don't hesitate, anyone, to make a call or chat if you want about any of the things discussed.
Thank you so much, Tom. We appreciate you.
Yep.
All right. Thank you,
Bye
everyone.
bye.
Have a great day.